All right, so here's video 2 on horizontal projectiles. So this time we have a ball rolling off at, say, 3 meters per second off of a table that's 1.2 meters tall. I have my calculator so I can get decimals now, right? And use 9.8. And so with this particular case, again, we know the ball is going to take this trajectory, the x velocity staying constant, the y velocity being different. So I'm going to got my x away here and my y over here. Remember, over here, just the kinematic equations are going to work. Don't try using speed, distance, time. Okay? No simple divisions are going to work like that, the type you do in speed, distance, time, or velocity, displacement, time. And over here, that's where you are going to use the velocity, displacement, time, and you don't need to deal with acceleration, initial velocity, or final velocity, because there isn't going to be any. Okay? Not unless we start more complicated problems where something does act, some other force does act on the ball as it goes down, maybe air resistance, or a magnet along the way that pulls it or something. Okay, so what are the things we'd be interested in knowing here? We're just determining how far away is it going to land? How long is it going to be in the air? How fast is it going to be going when it hits the ground? When it hits the ground, it's going to have an x velocity. It's going to have a y velocity. And when they add up, they're going to look like this, a diagonal, which is what's coming down. So we'll have to figure out the Vx and the Vy, and then we can do the Pythagorean on them, and that gives us that one there, okay? So pretty much we can figure out everything we need to here. All right, so let's get going. What do I know? I'm looking for delta x, V, I call it V, just leave it as V. I don't need to put V naught or Vx or anything like that really, because it's in the x direction, so you know, this V going to stay here. And this guy's V is going to stay there. I can call it Vx if you just want to reinstate that. That's still V in the x direction. So that'd be 3 meters per second. It's not going to change for the entire motion. Y, we know my delta y is going to be negative 1.2 meters. Okay, because our displacement is going to be below where I started. Negative 1.2 meters. Acceleration is going to be negative 9.8 today because I have my calculator. And the time is something we can find and kind of move around. I know my VI is 0. That gives me the 3 variables I need, so I can find whatever I'm looking for now. I decide I want to look for t, and so equation number 3 will work here. Again, delta y equals VIT plus 1/2 HE squared. This goes to 0, so I'm just going to get rid of that right away. And so delta y, which is be negative 1.2 meters, is equal to 0.5 times 9.8 times t squared. So negative 1.2 meters equals, and you guys have done this several times, negative 4.9 t squared. And so I will take the 1.2 divided by 4.9. I don't even put the negatives because I know they're going to cancel away when I divide them together. And so that gives me dividing both sides by negative 4.9 gives me 0.245. That'd be good enough. Let's round that. Here's what my calculator reads. All that junk, okay? But that's 3 digits is good. 3 significant digits is good. And so that is my t squared. So t would be the square root of that. And that would be 0.495 seconds. So there's my time, 0.495. I put that over here, t jumps over that ninja. And so now I can figure out my delta x easily here. delta x is going to be vx times t, and that would be 3 meters per second times 0.495 seconds. See, I forgot to put my S over here. Units. And so multiply my answer by 3. And I get 1.48 meters. Okay? So 1.48 meters would be the distance on which it would land. That's your delta x. Okay? Join you soon in the second video, or third video.